If you did not get to it, you need to get in touch with me. Stick around and talk to me after we end recording at the end of class. Overall, they were all right. There was one question that I was surprised. It was supposed to be one of those questions that was in there to be like a gimme, like an easier one. And I want to say that it probably fell on the mark of being the most missed question. So I'm going to just take a minute to discuss it if everybody's all right. I think everybody got a question that was along the lines of find the equation of a line through, and there was some point, let's say 8, -10, that's perpendicular to the line. And then there was something like x equals, let's say -2. And it threw me how many people started trying to use the point slope formula with a slope of -2. This x equals -2 is a line. And do you notice that line doesn't fit my y equals mx plus b? There's no y there. And so the comment I wrote, pardon me, most frequently was that that is a vertical line. Do you guys remember a line with its equation x equals a number is a vertical line? It has no slope. It's perpendicular to a horizontal line, which has a slope of 0. And so you could use the point slopes formula with a slope of 0. Y minus the y value is equal to m times x minus the x value would give me y plus 10 is equal to 0 times something. But that would just make y plus 10 equals 0, or y equals -10. And so you probably could have gotten to here without putting all of this work in the middle, if you remember that this is a vertical line, whereas x equals a number. It's perpendicular to a horizontal line, which is y equals a number. And the number would have to be the same as the y value of the point. And I was surprised how many people didn't remember that that is a vertical line. So perpendicular would be a horizontal line. So, but I digress. Other than that, I don't think there were many like across the board that folks weren't great with, but this one was a little concerning. I'm looking homework 8.1 is that date does not look right to me, the 15th, because the 15th is Thursday and your homework should not be due on the Thursday. Give me a second and let me double check that date for you. I apologize. It was late last night when I wrote it out. And so I'm sorry that I made a careless mistake there. I want to make sure that that date is right for you before we start looking at that new content. Before we start looking at that new content, does anybody have any other questions from the old stuff, the graphing the lines?
Can we do 3.1, number 18?
Sure. Give me just a second. So homework 8.1. Oh my gosh, it does say that's due the 15th. I am going to push that back to the 16th, which would be Friday. And I apologize that I've got that wrong date there. I will make sure that I change that. Before we do that though, You wanted to look at 3.1 number
18.
18. Write an equation in a standard form of a parabola that has the same shape as the graph f of x equals 7x squared, or f of x equals negative 7x squared. So it's going to be similar to one of those two. And do you notice that both of those two, the absolute value of that coefficient is 7. So our equation is going to have a 7 in it, but it's going to have the following number as a maximum. Okay, so that tells me that the turning point, or the vertex, is going to be where x is negative 9, y will be 2. So that's my vertex. If that's a maximum, that means that my parabola is opening downward. And so A will be negative. If it's got the same shape as this one, there'll be negative 7. And we're just shifting this one. We can look at it as using a transformation, shifting it to the, instead of having a vertex of the origin, having a vertex of negative 9, 7. Or we can use that vertex form of the equation where it's a times x minus h squared plus k, where hk is the vertex. So that'll give me, for a, we'll use the negative 7. X minus negative 9 would be x plus 9 squared, plus k, the y value of the vertex is 2. Does that make sense?
What is A?
A is, it would be negative 7 because they're telling us that it's going to have the same shape as this one.
Yeah, but what is A representing?
A, if we think back to when we were talking about transformations, when we started moving parabolas, well, I guess we started with a parabola, when we started moving parabolas around. Remember, we had said that if you had the graph of a times f of x, if a was bigger than 1, it stretched it tall and thin. If a was between 0 and 1, it made it squatty. And if a were negative, it turned it upside down. And so A is just that, how much I'm stretching or shrinking my parabola. And so because A is negative 7 and 7's a pretty big number, it means it's going to be like a tall, thin parabola stretched a lot. It's that stretch factor. If you give me a minute, I can try to look backwards in the notes to kind of refresh you on where we kind of talked about that idea.
So is that the answer?
Yeah,
Negative
that was
7?
the answer.
Weird. All right.
All right. Um, second. taking me forever to get there. I'm hoping I picked on the right date. Remember when we first started talking about parabolas? We started looking at a general parabola being y equals x squared. And we said that we could, if we added something afterwards, we moved it up or down. And if we added something in the parentheses, we moved it right or left. If we multiplied it by a negative, we turned it upside down. And remember when we multiplied by the number 2, we stretched it out, we made it taller, where it was the point 0, 1. After the stretch, it's the point, I'm sorry, where it was the point 1, 1. After the stretch, it was the point 1, 2. Where it had been 2, 4, it's now 2, 8. It's that coefficient of A has the net effect of stretching it. I think we had said that if we added something at the end, we moved it up. If we added something in the parentheses, we moved it left. Subtracting is right. And if we multiplied by a negative, we flipped it over. And if we multiplied by a number out in front, it was a stretch if the absolute value of that number was bigger than 1. And it was a shrink if that number was between 0 and 1. And so where that question had f of x equals negative 7x squared, that number in front, a, is negative 7, which means it's upside down and being stretched. So instead of going through the point 1, 1, it would go through the point 1, negative 7. It multiplies each of those y values by negative 7. And then from there, we went on, ooh, no, that's not what I want to do. We went on and said, well, that kind of can give us that vertex form where if the vertex is hk, we get a times x minus h quantity squared plus k. So that we're thinking of moving it sideways and up and down so that the vertex is hk. And that a tells us whether it's positive or negative, whether it goes up or down. But it also gives us an idea of how much it's being stretched. Can you remember being there a couple weeks ago? Actually, a little over a week ago.
Yeah.
And so that's what that question is kind of asking you to apply. All right? Because the vertex is always the turning point. It's always the maximum and minimum. So, all right. Anything else from any back homework or back concepts that anybody wants to look at?
Can we do the last two of the same homework?
We might just take the time to do one of them. The way you said last two, can I go on the assumption that the two questions are similar, or are they two very different questions?
They're both a pretty big pain in my ass.
Oh, you know what? No, we did this one in class. With the example that we did was almost identical to this. What you're doing is you're taking this piece of metal and you're folding it up to form this gutter. This gutter, when it's formed up, they're telling us that the cross section is a rectangle. So this is a rectangle. And they want you to see what you'd have to fold up to make that the largest area. And we had said, well, for a rectangle, area is length times width. Despite all of the geometry of folding that where they came from, they're telling you that this side is going to have that length x. And this side, they're saying, is 14 minus 2x. And so we can look at that area as being a function of x. When I distribute and rearrange, that's negative 2x squared plus 14x. Can you see that part of the problem?
Sure.
And so now looking at that equation, we recognize it's parabolic. That's negative, so it would be turning downward. And so it will have a maximum. And the maximum occurs on the axis of symmetry, where x is negative b over 2a. And so here, a is negative 2, so that would be 2 times negative 2. B is the coefficient on x, which would be 14, so that's negative 14. So that gives me negative 14 over negative 4, which would give me 3.5. And so it's maximized when the depth is 3.5 inches, and then we can substitute back in to find the area. All right. I do know that we picked, when we did examples of word problems from the book, we did actually the 2 word problems that are in the homework. So the other one works very similarly. Any better?
Yes, thank you.
Okay, you're welcome. Thanks for asking. Then I'm going to turn my finger back into a mouse. And hey, guys, guess what? Today we're changing a little bit and we're starting to look at that last unit. Unit 4 has 2 topics in it. The first is systems of equations. And after we look at systems of equations, we're going to look at an introduction to trigonometry. But today we're going to just start talking about those systems of equations. And when I talk about a system of equations, it means that we've got more than one equation. There are all sorts of different systems of equations. We're going to focus on systems of linear equations in 2 variables. So again, remember that my linear equation is first degree. We said it was something like ax plus by plus c equals 0. And we just spent a lot of time looking at linear equations. And we had said that if I have a linear equation, there's an infinite number of solutions. It would be all the points on the line. Now, if I have a system of linear equations, again, it means that I have more than one equation. And a solution is a point that satisfies all the equation. And so the first part of homework 8.1 asks you to determine if you have if a point is a solution. So to determine if a point is a solution, of a system, we have to check by substituting the point into all the equations. It must make them all true. Which I guess is just a kind of a fancy pants way of saying we're going to do a lot of checks to see if we have a solution. So my first example, I'd like to look at the system 9x plus 7y equals 18. There's one linear equation. And 8x minus 9y equals negative 69. Because I've got more than one equation here I have two, this would be my system of equations. And I might want to know something like, is negative.
Yeah, 1 second. I just want to be on the same page as you.
Okay. Let me know when you're ready.
Okay.
So we've got the system is negative 3, 5, a solution. And to answer that question, to determine, we have to check in each equation. Well, what are we going to check? If my point is negative 3, 5, I'll check x equals negative 3 and y equals 5. And again, I've got to do it in both equations. So if I have 9x plus 7y equals 18, my other equation is 8x minus 9y equals negative 69. I'm going to have to do two checks. First one, if x is negative 3, that would be 9 times x is negative 3, plus 7 times y is 5. And I want to know, does that equal 18? Well, I'm sorry. That shouldn't be 18. I apologize. That should just be 8. Can't read my own writing sometimes. So that gives me negative 27 plus 35, which is 8 equals 8. And that checks. But that's not enough. It's got to work in both equations. So in my second equation,
I thought the first equation was 18. Maybe I just read it wrong.
no, I just corrected it. I apologize. I wrote it wrong.
Oh,
It
okay.
should have been 8 and not 18. I apologize. Second equation, 8x is negative 3 minus 9y is 5. And I want to know, does that equal negative 69? 8 times negative 3 is negative 24. Minus 9 times 5 is 45. And that gives me negative 69. So it checks. And so here my answer would be yes, -3, 5 is a solution. And so does everybody get the idea of how to check? You have to check in both. If it doesn't work in either equation, then the answer would be no. If it didn't check in either equation, the answer is no.
If it satisfies one equation, would it still be true?
No. If it
It has
doesn't
to work for both.
any equation, the answer is no. So let's check. Let's do another one. Let's see. Is 8, 5 a solution of the system? 3y equals 2x minus 1 and 5x minus 4y equals 0. So here we're checking x is 8 and y is 5. First equation, 3y equals 2x minus 1 would give me 3 times y is 5. Does that equal 2 times x is 8 minus 1? Well, that gives me 15 equals 16 minus 1. That one checks. But now if I check in the other one, 5x minus 4y equals 0, that would be 5 times x is 8 minus 4 times y is 5. Does that equal 0? Well, 40 minus 20 is 20, not 0. And so here my answer is no, it's not a solution to the system, because in order to be a solution to the system, they both have to work. So if you get one no, if the first one would have been a no, you could have stopped there. And he knows it's not a solution. In order to be a solution, they all must be yeses. Better? In terms of solving these systems, we're going to have two methods that Mr. Blitzer focuses on in his book. He focuses on algebraic methods. And in addition, if you ever go on to take a course in linear algebra, you'll find that there are matrix methods of solving. And before we look at those algebraic methods, Mr. Blitzer doesn't look at solving by graphing. I'd like to take a minute, though, to show 3 examples solving by graphing, because I think they help you better wrap your mind around the different possibilities that can occur when we solve a system. So you're not going to see any graphing ones in the homework, but I would like to just talk briefly about to solve a system by graphing. What you're going to do is you're going to graph both equations on the same axes. And the solution is the point of intersection. Point or points of intersection. And again, I would like to take the time to show you three systems graphically, just so that you can wrap your minds around the different possibilities that can occur with these systems. So first example, let's solve by graphing. The system y equals -1/2 x plus 1, and y equals 1/2 x minus 3. Well, in the interest of time, for these examples, I put them both in slope-intercept form already. So for the first one, y equals -1/2 x plus 1. Does everybody remember that? Because that constant term b is 1. I begin at 1 on the y-axis. And since the slope is -1/2, from that point I go down 1/2, down 1/2. And this would be my first line. So that's my y equals -1/2 x plus 1. My second line, y equals +1/2 x minus 3. B, the y-intercept is -3. M, the slope is +1/2. So from here, I'll go up 1/2, up 1/2. And so this would be my line, y equals 1/2 x minus 3. And you notice they intersect at one point. And so my solution is that point for -1. And we could go through and check. But do you see how the lines cross once? I got one solution. Because I have one solution, this is considered a consistent system. And you see how if my lines cross once, I got one solution. Life is good. Next example. Let's solve the system. Y equals 2x plus 3. And y equals 2x minus 2. First line has an intercept of 3 and a slope of 2, which would be 2/1. So from here, I'll go up 2/1, up 2/1, and draw my line. This second line has an intercept of -2. It also has a slope of 2/1. So this time I'll begin at -2, but I'll still go up 2/1, up 2/1. And what do you notice about those lines? Will they ever intersect? You guys are awfully quiet. Do you notice that they're parallel lines?
Yeah, they'll never intersect.
They never intersect. So the system has no solutions. Because it has no solutions, it's considered an inconsistent system. Instead, if I were to solve algebraically, we'll know something's inconsistent if we get a false statement. What do I mean by a false statement? Something like if I were to say 3 equals 4. We know that's false. So that type of solution would tell me that I'm inconsistent. And so does it make sense if I consider lines? I could have lines that cross in one point, unique solution, I got it. But I could also have lines that never cross. And so it's possible to have systems with no solutions. One more of these graphing. This time, let's solve graphically. And this time, let's have our solution system be y equals 2x minus 3 and 3y equals 6x minus 9. And so I can graph that first line right away. It's in slope-intercept form. I begin at -3. And my slope is 2/1. So from here I go up 2/1, up 2/1. And I have my line y equals 2x minus 3. Everybody all right with that one? My second line, well, where I have 3y equals 6x minus 9, I'd want to start by putting that in slope-intercept form. To get y all alone, does everybody see the need to divide both sides by 3? And that gives me y equals 2x minus 3. So this would begin at -3 and have a slope of 2/1. Begin at -3 and have a slope of 2/1. Wait a minute. Don't those two lines fall on top of each other? Since the lines have the same graphs, they intersect at all the points. On the line, it tells me that I have infinite solutions. The solution set would be the set of all pairs x, y, such that And we could put either equation, y equals 2x minus 3. It's a way of saying that the solution are all the points on the line. Here, where we have infinite solutions, this is considered a dependent system. And so do you see how with these, there's three possibilities. If the two lines are the same, there's infinite solutions. If the two lines are parallel, but they have different intercepts, they don't cross at all, there are no solutions. And if the lines aren't parallel at all, I just have one solution where they intersect. Going back, I'll know that a system is dependent, solving algebraically. You'll get an identity. An equation that says something like 4 equals 4, something's equal to itself. So dependent systems have infinite solutions. Independent solutions, inconsistent, systems have no solutions. Consistent systems have one solution when we're dealing with linear equations. And so, again, the only reason I do these graphing examples is because it helps me better wrap around my mind around the idea and how sometimes I have one solution, sometimes I have no solutions, and sometimes I have infinite solutions. Is everybody okay with those concepts? Any questions? Not hearing any then. Next, we're going to look at how to solve algebraically. And to solve algebraically, we're going to have two methods. The first method is by substitution. And again, why would I want to solve them algebraically? I don't always have a piece of graph paper in my back pocket. Also, if I were to intersect at points whose coordinates were fractions, that would be really hard to read off the graph. So to solve by substitution, the first thing that we want to do is we want to solve one of the equations for one of the variables. And the reason this is called substitution is because what we're going to do next is we're going to substitute that expression in for that variable in the other equation. So we'll substitute the resulting expression for that variable in the other equation. That'll give us an equation with one variable. So we're going to solve that new equation that we formed. But when we do that, we'll only know half of the answer. We'll only know one of the variables. So we'll have to back substitute in any of the preceding equations to find the other variable. And then lastly, because we want to know we got it right before we turn our paper in, we're going to check in all the original equations. So that's our cookbook steps. Are we ready for an example, or do you guys need me to hold off for a second? Not hearing any concerns. We're going to start with a real simple example. X plus y equals 6 and y equals 2x. What makes this a simple example is that we're already solved for y in one of the equations. And honestly, when I already have one variable solved for, that's when I'm most likely to use my substitution. So this one's already solved for y. So in my other equation where I have x plus y equals 6, I can replace the y with what it's equal to, 2x. And so here I substitute it for y in my other equation. Well, that equation is pretty easy to solve. X plus 2x is 3x equals 6. And so solving, I get x equals 2. So I solved for the one variable. But I still have to find the other variable. And to do that, I can use any of the equations. But being I'm looking for y, I find the one with y alone the easiest one to use. So if y equals 2x, we'll substitute y equals 2 times 2. And so I get y equals 4. And so my solution would be the point x is 2, y is 4. And so when I check, first I have to check in x plus y equals 6. Well, if x is 2 and y is 4, 2 plus 4 equals 6, and it checks. Then I have to check in y equals 2x. Well, if y is 4 and x is 2, 4 equals 2 times 2, and it checks. That one, all right. Let's try another then. Next example, let's solve using substitution. (2x minus 3y equals negative 13, and 2x minus y equals negative 7. Here, it's not clear. I don't have one variable alone. And again, if I'm using substitution, I like to try to solve for the variable with a coefficient of 1 if one exists. So over here, I'm going to solve this equation for y. So I have 2x minus y equals -7. To solve for y, I'll subtract 2x from both sides, giving me -y equals -2x minus 7. Not quite done. I'm going to divide both sides by -1. And I get y equals 2x plus 7. Everybody all right to there? Then I'm going to take this and substitute for y in the 2x minus 3y equals -13. That'll give me 2x minus 3 times, well, what's y? Y is 2x plus 7 equals -13. That'll give me 2x, let's see, I gotta distribute here, minus 6x minus 21 equals -13. So that'll give me -4x minus 21 equals -13. So adding 21, I get -4x equals 8. And dividing by -4, I get x equals -2. Now, I've got to find y. To find y, I could go back and use either of these equations, but don't tell anybody I'm owning up that I'm lazy. I think it's easier to use this equation. Y equals 2x plus 7. So that would give me y equals 2 times -2 plus 7. -4 plus 7 is 3. And so I'd say that my solution is -2, 3. But again, I'd have to check in my original equations, 2x minus 3y equals -13. And the other one was 2x minus y equals -7. So if I'm checking -2, 3, for x, I'll put in -2. For y, I'll put in 3. So that's -4 minus 9, which is -13, and it checks. Here, 2x is -2 minus y is 3. Does that equal -7? -4 minus 3 is -7, and it checks. How is this solving by substitution? Let's have you folks try one. Let's have you folks solve by substitution. And let's have 2x plus 5y equals -4. And 3x minus y equals 11. And I'm going to be quiet and give you about 3 minutes to work on that. Do you folks have it, or do you need more time?
Another minute.
Okay. Let me know when you have it, or if you have it. Did everybody get 3, -2?
Yep.
Great. Then, if we're okay with solving by substitution, next thing we're going to look at is to solve by, sometimes it's called the addition method. Sometimes it's called the elimination method. But I like to call it magic. In order to solve this way, the first thing that we want to do is we want to put both equations in ax plus by equals c form. So what does that form mean? We want the constant alone on one side. We want the variable terms in alphabetical order. Then the second thing we're going to do is we're going to multiply 1 or both of the equations or equations, so I'll put that S in parentheses, by a constant or need be different constants, so that the coefficients on one of the variables are opposites. So we want them to have different, same number, different signs, same absolute value, I guess we should say, different signs. Once they're like that, we're going to, it's called the addition method because we're going to add the equations. When we add the equation, one of the variables should be gone. One of them should be eliminated or it disappears, which is why I call it magic. And so we'll solve the resulting equation. But that'll only give us one of the variables. So we'll have to back substitute, pardon me, to find the other variable. And then again, we have to check in all the original equations. Oh my heavens. What's that all about? Again, I find this method easiest, especially if my original equations are all in that standard form. Are you folks ready for an example or two?
Yep.
So for my example, let's look at the system 2x minus 7y equals 2 and 3x plus y equals negative 20. Now here, you have some choice. Some people might choose to try to eliminate the x's and get their coefficients to be opposites. Some people might choose to eliminate the y's and make their coefficients opposites. I would probably do the latter because you see over here, this one's got a coefficient of 1. This one's got a coefficient of negative 7. Well, I'm going to take that first equation and just leave it alone. Going to keep that as 2x minus 7y equals 2. But now that second equation, I'm going to multiply both sides by 7. Because when I do that, that gives me 21x plus 7y equals negative 140. And you see why I chose that 7 is because now these coefficients are opposites. One's positive 7, one's negative 7. So now that they're opposites, make sure my equal signs are lined up. If these are equal and these are equal, their sum should be equal. And when I add down, I get 23x minus 7y plus 7y is 0y, and there are no y's left. So what I've done is I've eliminated the y's. Or I did my magic, I made them disappear. So now I'll finish solving, dividing both sides by 23. I'll get x equals negative 6. But sadly, I'm not done. I still have to find y. To find y, I can use any of the equations that are here. I'm going to take that 3x plus y equals negative 20. And I'm going to substitute negative 6 in for x to find y. Gives me negative 18 plus y is negative 20. And adding, I get y is negative 2. So my solution is the point negative 6, negative 2. And again, I would have to check into both the 2x minus 7y equals 2 and the 3x plus y equals negative 20. So when I check 2 times -6 minus 7 times -2, well, that's -12 plus 14, which is 2, so it checks. And when I check 3 times -6 plus -2, that's -18 plus -2 is -20. So it checks. And so that's the general idea of that elimination or addition method. I'm looking at the clock and we only have 3 minutes left. And to try to squeeze another example in 3 minutes would just be me talking really fast at you. Can you sort of wrap your mind around the idea of these? On Wednesday, we'll look at more examples and we'll also look at word problems, because these 2 equations and 2 variables is a very convenient way of solving an awful lot of real life situations. Any questions on what we did today? If not, Azim, I've got that you're here. Taylor, I've got that you're here. And Cameron, I think you were in before and just got booted. Yeah.
Yeah.
Okay. Any questions?
Nope.
I'm gonna
No.
stop recording. If anybody had